All right, so welcome to the end of week 3. After today, we're going to be a quarter of the way done with the quarter. Look at that, we're flying by. So today's plan, I want to actually do some examples of probability. We talked a lot about it last time in terms of the ideas behind probabilities and what the different words mean, and versus or, conditional probabilities, what it means for things to be dependent, independent, mutually exclusive, blah, blah, blah. Well, we'll play around a little bit with that so we can get the feel with some examples. And then we'll start talking about what we call probability distribution functions, PDFs, a little bit different than the file format. But PDFs are huge. Probability density functions are basically what statistics are built on. So we're going to start dipping our toe into that. We'll look at one called the binomial distribution today. We'll see how far we get. I don't think we're going to get beyond that. But that's the goal on my end for today. But I do want to start, as always, opening up to any questions about what we've talked about so far, or any homework questions, anything you guys would like to talk about. All right, well, hearing none and seeing none, then I'm going to go ahead and dive back in. So give me just 1 second and I'm going to go switch to the whiteboard. I'll see you in just a moment. All right, sorry about that. Just had to adjust something on my phone. All right, so let's practice with probabilities. Let's actually look at some real things and see if we can figure out probabilities and talk about all the things we looked at last time, so we understand how to deal with conditional probabilities and ands and ors and all that good stuff. But we'll start off easy. Start off easy just to kind of warm up and remind us how these work. Right, so remember, in general, when we want to calculate a probability, what we look at is the number of outcomes of the thing that we're interested in, and we divide that by the total number of possible outcomes. So it's really just a measure of relative frequency, right? And I think I mentioned that last time, that probability is a long-term relative frequency. It's what do we get in the long term? How often would these things occur? All right, so we'll start off with a nice easy one, kind of warm up our brain. But let's say we're going to pick a month at random out of the year. Okay, so we're going to put all the months' names on just, maybe scraps of paper, put it into some bin, reach in and pull one out. Okay, so we're just going to pick 1 month. And so here's what I would like to do. I would like to figure out what's the probability that if we pick 1 month, if we randomly pick 1 month of the year, that it has 31 days. Okay, so what's the likelihood that if we just randomly pick a month, that it's got 31 days in it? All right, so let's just think about how we're going to build this. We need to know 2 things. We need to know how many months have 31 days, right? How many possible outcomes are there that are let's call it a success, right? That we got 31 days. So we need to know that. And then we need to know the total number of possible outcomes. So if I reach in, how many, and grab something out, how many total different possibilities are there? So let's start with that because that's really easy, or should be. How many possible outcomes are there?
12.
12.
Or
There's
7
12
over
months.
12, I think.
So there's going to be 12 different months we can pick, anything from January through December. So the bottom of our fraction here for this probability is going to be 12. All right, so now comes the more difficult part because most of us don't just have this information right on top of our head.
7.
Now we got to count up how many of them actually have 31 days. So who was that just said 7?
That was me.
All right, Elisha. Okay, so you counted up. We have 7 months that have 31 days.
I hope so. Hold on now. Let me pull out the calendar here.
Okay, so we can pull out the calendar or whatever. Okay, well, we know February does not, right? February's got 28, sometimes 29 in a weird year. I know a little rhyme for knowing which days have 30. It's 30 days, half September, April, June, and November. So I know those do not have 31 days. But yes, if we count them up, there are 7 that have 31 days. Have you seen the knuckle trick? Let me show you this one for month lengths. So if you start on one end, so I'll start so that it's relative to you. Allie, you know it, nice. So if you start over here with this knuckle, this is January. Then there's a dip for February. Then you're back on a knuckle for March, a dip for April, May, June, July. Carry it over here is August, September, October, November, December. Well, it turns out that all of the ones that are on your knuckles have 31 days. Where's my daily Star Wars shirt? Check it out, man.
That's a Millennium Falcon behind that. It says Hans, not Vans, man.
Yeah, it's all good. It's all good. But I love the fact that we now have something to look forward to. The question is, what's it going to be? I'm going to have to buy some more shirts. I don't have enough for one different one each day. Anyway, all right. So if you just count them up, January, March, May, July, August, October, November, or wait, August, October, December. So that's 7. And so, yes, the probability of actually randomly picking a month that has 31 days is 7/12. So 7 times out of 12 on the long haul, you will pick a month that has 31 days. Okay, so nice and easy for certain things, but it really is, we have to count up how many different possibilities are there and how many of them give us what we want. All right, well, let's do one that's a little bit more complicated, a little bit more difficult. So how about this? We're going to roll a pair of dice. So my question is, what is the probability of rolling a 9? All right, so I got my pair of dice. I roll them. And what's the likelihood that that's a 9? All right, so same general question, right? Trying to find probability. So we need to approach it the same way. We need to figure out 2 things. The first is, how many different ways are there to get a 9? Right, that's going to go on top. And then the other thing we need to know is, how many different rolls are there? How many different possibilities are there? All right, so let's see if we can figure that out. So I don't know if any of you guys play dice games. Obviously being in Tahoe, some of you may be familiar with like craps and stuff that are at the casinos, But a lot of you may have also played things like Monopoly or Parcheesi or whatever, insert favorite board game here that uses dice. So, or actually one of my more favorites is Settlers of Catan. I don't know if anybody's a Catan player. But anyway, so what's the probability of rolling 9? So let's start with what is the total number of possible outcomes? So how about this? I roll a pair of dice, right? No, I lost my die. So I roll a pair of dice. What are the different numbers I can get? Like, what's the smallest total I can get?
2.
2, right? If I roll snake eyes, I roll a 1 on each of my dice, and get a 2. So that's the smallest I can get. Obviously, I could get a total of 3. I've got a 1 and a 2. I can get a total of 4, and they keep getting bigger and bigger and bigger. What's the largest I can get?
That's what you think.
Right, would be 12 boxcars, right? Get 2 6s, I get 12. But I can get everything between 2 and 12. All right, now you got to be careful here because some people will go, all right, if I can get every number between 2 and 12, and I just count those up, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 11 different number combinations. The thing is that there are more than 11 possible results here. This one's a little bit tricky. Does anybody know how many actual total results we could get?
36, possibly?
Yeah, it's 36. Where's that come from, Elisha?
Taking the number of dice and multiplying them together?
Okay, so you think about the different options. The first die, I have 6 different numbers I can get. For each one of those, there are 6 different numbers I can get on the other die. Now, sometimes it's a little bit easier to see this. I'm going to replace my die with another one. So we've got 2 different dice, a red one and a white one. Okay, so let me show you, for example, rolling a 4. So here are the different ways you can roll a 4. So there's a 4. Red on the 1 on the red, and a 3 on the white. I also can get a 4 this way, a 2 on each die. But I also could get a 4 this way. So if we were to look at just the different options for 4, there are actually 3 different ways we can get it. Right? 1 and 3, 2 and 2, and 3 and 1. So it's a little bit more complicated than just counting up which different possibilities are, because for each one of these there are 6 choices, right? So here's a red 1. I can get white 1, white 2, white 3, white 4, white 5, and white 6. So there were 6 different choices when red is 1. Well, if red is 2, I can do the same thing, get all 6. When red is 3, I can get 6 more. So I get 6 plus 6 plus 6 plus 6, right? And I do that 6 times. We know that's multiplication. It's 6 times 6 is 36. So for this guy, it turns out that the denominator for our probability is going to be 36. 36 possible outcomes. All right, so there are actually quite a few. But now the question is, how many of those are 9s? Well, let's use our dice and get some 9s. So here's one version of 9. Right? So Allie just threw up in the chat, she wrote 3, 6, 6, 3, 5, 4, and 4, 5. And that's exactly right. So here's 6, 3. I can have 5, 4. I can have, where am I? 5, 4. Let's see. So I can have 4, 5, or I can have 3, 6. So it turns out that there are actually 4 different ways that we can get a 9. So our probability of rolling a 9 is actually 4 out of 36. And again, if you're not really sure about that 4, here they are. You can have 6 and 3, 5 and 4, 4 and 5, and 3 and 6. So the 6 and 3 and the 3 and 6 are different. Those are different things, because you can think of the first one as the first die, the result on the first die, and the second number is the result from the second die. All right, well, let's go ahead and reduce this. So we go from 4 over 36, you can divide those both by 4, and you get 9. So on average, long term, when you roll a pair of dice, you're going to get a 9, 1 out of every 9 rolls, approximately. Right? Does that mean that you will get 1 roll of 9 if you do this 9 times? No. You might not get any. You might get 2. You might get 5. That'd be pretty rare, right? But a 9 is only 1 out of 9 times. Well, it turns out the most likely is 7. 7 happens the most. It happens 6 different ways. So it's 6 out of 36. And as you move further from 7, it becomes less likely. In fact, let me do this for you. Let me actually just construct a frequency diagram or a frequency chart for rolling dice. Okay, so this is going to be the number, and this is going to be their frequency. All right, so 2, there's only one way of getting it, 1 and 1. 3, you can get that 2 different ways, 1 and 2, 2 and 1. 4, you can get that 3 different ways. I showed those to you, 1 and 3, 2 and 2, 3 and 1. 5, there's 4 ways. 6, there's 5. 7, there's 6. And then when you get to the other side, and I don't have quite enough space here to do them all, they start going back down. So a 9 is just as likely as a 5. It's exactly as likely as a 5 because it has the same number of combinations that get given. Right? I can finish this. I'll run these over here. So 11 and 12. It's killing me not to complete it. All right, so 11 can happen 2 different ways, and 12 can happen just the one way, 6 and 6. So you notice that with this frequency diagram, it actually helps us get the probability. Probability of 9 is 4 out of the total 36. All right, so for those of you who play Catan, and I forget who it was, somebody said they love Catan as well. Catan, the numbers, you put little number discs on the different tiles, and if those numbers get rolled, you get the resources from them. But you'll notice if you look at them, they have dots on that disc, and the dots correspond to their frequency. So the 2 and the 12 will just have 1 dot on it. The 3 and the 11 will have 2 dots, and so on. And then the ones that are most likely are 6 and 8, and they even color those differently to draw your attention and go, oh yeah, 6s and 8s. You want to get 6s and 8s. Anyway, so there's your probability of rolling a number. All right, well, I think that's all I want to do for just basic probabilities, because we should probably talk about the other things. What about and? What about or? What about conditional, right? What about those kind of probabilities? So let's start with or. And we'll even use the dice example to do an or. Okay. So how about this? We're still rolling a pair of dice. But this time, I want to know, what is the probability of rolling a 7 or a 11. Okay, so what's the probability of getting either a 7 or an 11? So if we were going to write this in the notation that we use for probabilities, we'd write it like this. Remember, the big P tells us we're finding a probability. So it's the probability of a 7 or an 11. Okay, so hopefully you remember or is the one that's less restrictive. It's more likely to happen because we're saying it's totally cool if we get a 7 or if we get an 11. So either one of those is going to make this more likely.
So would we add it together,
Okay,
the
so-
frequency?
Yep, so this is the one where we're going to add them together. Now it does matter if they are mutually exclusive or not. So mutually exclusive means they both cannot happen at the same time. And this is a case of mutually exclusive. If I roll a pair of dice, there's no way it's going to add up to 7 and 11 at the same time. Right? That's impossible. So mutually exclusive is the nice one, because what we can do is just take the probability of a 7 and add it to the probability of 11. Okay, but we can only do this since they're mutually exclusive. We'll look at an example in a little bit where things are not mutually exclusive, and we'll see why it's easier if they are mutually exclusive. All right, so let's get our probabilities here then. So the probability of 7, well, there are 6 different ways of getting a 7 out of a total of 36 different possibilities. For the 11, we look at our chart, it's got a frequency of 2. So that's going to be 2 out of 36. So I'm not going to reduce these fractions yet. I'm just going to go ahead and add them since they've got a common denominator. And so we get that the probability is 8 out of 36. We probably want to be good and reduce that by dividing by 4. And so it's 2 out of 9. As a percent, that's 22.2%. So somewhere in the 1 out of every 4 or 5 times, you're going to roll a 7 or an 11. Okay, so this is the big thing for or, right? Remember, for or, we add the probability. Okay, now, I can't really do a probability of and. I mean, I guess we can. It doesn't really make much sense with dice, but let's just, for the sake of doing it, suppose you are asked, what's the probability of rolling a 3 and an 8? Okay, so we're going to look at the probability of 3 and 8. So how likely is that? If I roll a pair of dice, how likely is it that the total will be 3 and 8 at the same time?
That's impossible.
Okay, so that's impossible, right? If I roll the dice, I either get, if I roll an 8, that's not a 3. It's not a 3 at the same time. So it's impossible for it to be an 8 and a 3 at the same time. Just like if I were to roll a 3. Okay. But it's not 8 at the same time. So it actually is impossible. So what does that make the probability? Do you remember? Awesome, thanks, Ceremony. So the probability of something that's impossible is 0. All probabilities are between 0 and 1. 0 is impossible, 1 is guaranteed. Okay, well, again, that's because they're mutually exclusive. If two events are mutually exclusive, they cannot both happen at the same time. The probability of the and statement is going to be 0. All right, so that means we need to have another example, because if we try to do anything with ands, they're not going to work. Also, conditional probabilities, this is a bad case because it's not like your roll depends on another roll, right? If I take a pair of dice and I roll them, it doesn't have an effect on the next time I roll the dice or the next time or the next time, right? If they're fair dice in it. So let's look at another example. And this time, let's say we go out and we poll 100 people. And we just ask them their opinion on should women be allowed to serve in combat? Okay, so we're just going to ask their opinion, and it's simple, just yes or no. So I go up to you and I just say, hey, I'm doing the survey. I would just like to know, do you believe that women should be allowed to serve in combat? They tell me yes or no. I write it down on my chart. I gather my information. Okay, so again, this is completely hypothetical. I did not do this. It's not like I went down to Rayleigh's and just started asking the first 100 people I saw using convenience sampling, right? Or it's not like I ask every third person coming through the door, systematic sampling, right? No, I didn't do this. I just made up these numbers, all right? But I'm going to give it to you in a table, just because it's a little bit easier that way. So here's going to be the responses, and I'm going to separate the answers or the responses by whether it was a man or a woman that I asked, whether it was male or female that I asked. All right, so we're going to have 2 rows here, one for male or female, and then there are going to be 2 columns, one for yes and one for no. And so I go out and I ask these people, and I get 22 and 28. And let's say I get 40 and 10. Okay, so if you add up all of these numbers, you get 100, right? So I asked 100 people. So these should add up to 100. That was the plan. It definitely looks like it, yeah. Okay. So this right here, just so you know, because you'll come across this phrase when you're reading stats books or doing homework. This is what we call a contingency table. Basically, it's just storing the information, right? But this is a contingency table. I need to allow myself some more space. All right, now, another thing that you will often see with a contingency table is another row and another column that holds the totals. All right, so I'm going to put another line here that says total. And the same thing over here. And so this is what it would look like. You'd see in the columns, the sums of the columns. So 22 and 40 would be 62. 28 and 10 would be 38. So basically what this would allow you to do, the reason that you'll see this is it's really quick to help you see total amounts. So there are, of my 100 respondents, 62 said, yes, they think women should be able to serve in combat. 38 said no. It's a little bit faster to just be able to look at that column than to try to add things up. Right? And then you'll see the same thing in the if you go across the rows. So 22 and 28 is 50, as is 40 and 10. So what this says is that when we ask these 100 people, it turns out that 50 of them were men and 50 of them were women. So we actually have an equal number of respondents from both genders, but there you go, there's 50. And then what you'll usually see down in this one right here is the total of the row or the column of the totals. So in this case, it's 100. And if this is done properly, what's nice is this guy down here is always the number of our sample. Right? Remember, we call that N. So it's kind of nice in a contingency table. You can jump right down there to find out what's your total number. All right, so looking at this chart, let's see if we can figure out some probabilities. And again, we'll start easy. If we were to just grab one of these people at random, what's the probability that they said yes? So what's the probability that someone that we pick at random says yes, they believe women should be able to serve in combat? All right, got a bunch of people throwing stuff in the chat box. Awesome. It's 62 out of 100. All right, so we're going to look at how many were yeses, because that's what we're counting up. Well, that was 62. 62 of the people said yes. And the total number of outcomes, the total number of people was 100. So it's 62 out of 100, or 31 out of 50. 62%. Okay, so it's really easy if you just want to find the probability of yes, no, male, female. Like it's pretty fast. All right, but let's do this. Let's vary this up and do some other probabilities that involve and or, things that involve conditions and so on. So here's the next one. How about what's the probability of male and no? So what's the probability that if we go and ask somebody, or just go and randomly grab one of these 100 people, what's the probability that they were male and said, no, I do not think women should be able to serve in combat? Okay, now, if we don't have it as a contingency table, it can be a little bit trickier. But this is actually pretty fast. And I already saw it pop up in the chat box. I think that was Ali. I didn't actually read quickly enough. I think it was Ali. Here's what you can do. We want male and no. Well, we've got that number. The number of males who also said no is 28. So with this contingency table, we're able to recognize that the probability that this person is male and says no is 28 out of 100. So here's the trick. If you've got this set up, if you ever have an and, basically go across the row, go down the column until you find the square that holds the number for both of them. So what about if we wanted the number of women that said no? So the probability of female and no, female no, boom, 10. Female yes, 40. Male yes, 22. It's really fast. Okay, so there's male and no. All right, but I want to show you where now we have to be a little bit careful when we do and. I don't know if you remember there was a formula, or actually, never mind. I lied. We're gonna just I meant or. Let's go to an or. Let's go to the probability that we have someone who's female or no. Now, when we did this before, remember when we were rolling the dice? What was the trick for the or? What did we do there? I mean,
Add 'em up.
Yeah, I was going to pick on Elisha because he was the one who said it, but that's right. We're going to add them up, right? So we saw before that we're going to take, this would be the probability of female plus the probability of no. All right, well, if we do that here, we're actually going to get the wrong answer. Okay, but let's just look at what this would be. The probability of female, what's the probability of female? What's the probability that if we pick one of these people at random, that they're female? Okay, so Ali, the 50, that's the frequency. That's how many of them are female. To get the probability, we have to do something with that 50. Yeah, good. We got to divide by 100. So the probability that they're female is 50 out of 100. And again, you can just go over to the female, total is 50 out of 100. Okay, so what about no? What's the probability that someone says no?
10 out of 100?
Not 10.
38?
It's going to be 38. Yeah, I totally see where you got that 10 because the 10 was the females that said no. But we're just looking for total, like how many people said no, and it was 38. So we have plus 38 out of 100. All right, now, if they're mutually exclusive, this is the correct answer. But this time they're not mutually exclusive. Is it possible that there is a female who says no? You should all be bobbing your heads. Absolutely, right? Go back to the 10, right? I think that was Ashton who gave me the 10 earlier. All right, that 10, there were 10 females that said no. So these are not mutually exclusive anymore. And because they're not mutually exclusive, we actually have to subtract from this the probability of the and. What's the probability that they're female and say no? So we actually have to have a minus here. And the female and no was that 10. So we're going to subtract off that 10 over 100. All right, so I'm going to write here, not mutually exclusive. Not mutually exclusive. We can't use that, or we can't just add those two. We have to subtract off this other one. So the actual answer, if we take these 50 plus 38 minus 10, that's 78. So there's a 78% chance that if we randomly pick somebody, that they will either be female or think that women should not be able to serve in combat. All right, so why do we have to take that off? You guys remember my reasoning for that last time? Or even if you don't remember my reasoning, do you see why we have to take it off?
Yes.
Yes, you want to expand on that? Why?
Oh yeah, sorry.
That's
Because
okay.
because the 38 is like counting, like you said, not mutually exclusive. Or are you talking about the last lecture, or are you talking about like a couple seconds ago?
I'm talking about the last lecture.
Oh, never mind, sorry.
Oh, that's okay. Well, check this out. So think about that 50. That 50 came from adding the 40 and the 10. Right? That's how we got that 50. The 38 came from adding the 28 and the 10. And so if I add those together, I actually counted that 10 twice. Right? I counted it once as I went across the row, and I did it once as I went down the column. So it got double counted. Those 10 people got double counted when I did these two numbers. So if I want to be accurate, I have to get rid of that double count. And so I take it away. Right? If I put it in twice, I got to remove it once. And that's why I subtract it off. So when you have an or and things are not mutually exclusive, you have to subtract the probability of the and because you double counted it. So in a contingency table, it's really easy. You just take that row, that column, add them up, and subtract the box that was in common. But that's how we can get the probability of or. All right, so any questions on or before I show you a conditional probability? Okay, looks like we're good. So how about we try this one? Let's go with, what's the probability that the person says yes, given that they're female? So again, remember what that vertical bar means. This is saying it's a conditional probability. All right, so what's the probability that a person said yes, given that that person is female? All right, so conditional probabilities tend to be the ones that cause the most trouble for folks. So let's kind of work through this and give you an idea of how to do this. So here's what I do. The first thing I do is I look at the condition. Right? In this case, the condition is the person I pick has to be female. So when I build my probability, when I actually go and do this thing, I know that the bottom of this fraction, the denominator of this fraction, is going to be the number of females, which in this case is 50. Because I don't have all 100 anymore. I've already said, oh, the woman I was talking, or the person I was talking to was a woman. Oh, okay. So we ignore all the men. I don't care what happened with the men. I'm only concerned with the women. And I know that the women, there were 50 of them. So that restricted, right? I went from my 100 total people down to just 50 females. All right, so now the question is, of those 50 females, how many of them said yes? Well, where are you going to find that on the chart? What number is that? The number of females that said yes. All right, so I'll just put in the chat box 40. Good. That's what this is right here, right? This is the number of females who said yes. So this probability is going to be 40 out of 50. Now, if you want to write those as a formula, because sometimes people like to see this as a formula, this is basically saying, all right, the probability of yes and female, or given that it's female, it's equal to, well, on the bottom, this was the probability of female. And on top, this was the probability of yes and female. So there is a formula for finding probability and conditional probability, and I think I gave this to you last time, right? Probability of A given B is the probability of A and B over the probability of B. If I didn't, that's what this is saying. But when you've got a contingency table, it's actually pretty nice. All you have to do is look at the row or column of your given, and then look within that row or column for how many of them said yes or said no or whatever. All right, obviously we want to reduce that down, but we'll leave it as 40 out of 50. So it changes the denominator, changes the bottom. As soon as you make it conditional, you got to change the bottom number. All right, so that was the probability of yes given female. So let's do one more. What's the probability that someone is male given that they say no? Okay, so what's the probability that someone is male given the fact we know that they said no? All right, so again, I'm not looking at all of the people. I'm only looking at those that said no. All right, so what's the denominator going to be? What's the bottom of this fraction going to be? How many people said no? Good, it's 38. There were 38 people that said no. All right, so of those that said no, how many of them were male? All right, good. So how they just put in the box? 28. 28 are the males who said no. So there's the probability that someone is male if they said no. All right, so conditional. Just restrict yourselves to, okay, I'm only there. I've reduced my number of possibilities, but then within those possibilities, what do I have? All right, so there's using a contingency table. Let's do a couple more conditional, but using playing cards. So we'll go back to the playing card example. So how about this? What's the probability that I draw an ace given that the card is a diamond? So I'm just going back to my standard deck of cards. I happen to still have it here with me. So here's my standard deck of cards. So the question is, What's the probability of getting an ace if I know the card is a diamond? So let's think about that. We have to restrict ourselves just to the diamonds. So I'm going to go through the deck, and every time there's a diamond, I'm going to pull it out. Right? So another diamond. There's another diamond, right? And so on and so forth until I get only the diamonds. So then once I have only diamonds here, what's the probability that I pull out an ace? So let's start with the restriction, diamonds. Does anybody remember or know how many diamonds there are in the deck?
There's 12. Sorry.
You want to go with your first guess?
13.
Yeah, there are 13. Right, there are 13 of each suit, ace through king. All right, so there are 13 diamonds. All right, so that means that when we calculate this conditional probability, the denominator is going to be 13. Okay, now of those 13, how many of them are aces? Yeah, just the one. There's only one ace of diamonds, unless you've got some weird deck, like if you're playing pinochle or something. But yep, there's only one ace of diamonds, so your probability of getting an ace, given that it was a diamond to start with, is 1 in 13. All right, so that's the conditional probability of an ace given a diamond. So let's turn it around. Let's calculate the probability of getting a diamond given that the card is an ace. So I'm going to do the same thing. I'm going to take my deck, I'm going to sort through it, but instead of finding all the diamonds, I'm going to find all the aces. Okay, well, I should be able to do that pretty quickly here. He says not seeing a single ace anywhere. Oh, there's 1, 2, 3, and there's the other one, 4. Okay, so I go and I sort through and I get all the aces. They're there. There's only 4 of them. Ace of hearts, ace of spades, ace of clubs, ace of diamonds. All right, so that means the bottom of this fraction is going to be a 4, because I've only got 4 aces. All right, so what's the probability that if I just draw one out at random, that I get the ace of diamonds? Well, how many aces of diamonds are there? Yeah, it's the same answer as before. It's 1. So the probability of getting a diamond, given that the card is an ace, is 1 out of 4. So I wanted to do this one just to show you that it matters the order. Oh my gosh, it matters the order, right? Whether we're talking about an ace given that it's a diamond or a diamond given that it's an ace, greatly changes those probabilities. This one is much more likely. It's over 3 times as likely than the other. So we definitely have to be careful with the order. You got to make sure you're following the order. So the way to remember it is the second one is your restriction. So that's giving you the bottom number. The first one is your top number. All right. So there are your conditional probabilities. Real quick before we leave this, because there's something else I want to remind you about. How about this probability? Just with a whole deck of cards, this isn't going to be conditional or anything. What's the probability of just drawing an ace? So we're going to go back to the full deck. All right, it's not restricted anymore. I got everything there. So what number is going to go on the bottom here? How many cards in the deck?
52.
In the standard, if we don't have jokers, or like I said, we're not playing pinochle or something. So there's 52. And then how many aces? I already saw Bruno gave us the probability there. So there's 4. So it's 4 out of 52. All right, what about the probability of a diamond? Well, again, the denominator is going to be 52 because there are 52 cards. How many diamonds were there? 13. Good, thank you. So that's 13 out of 52. So these are the non-conditional probabilities. That's just the probabilities in general. But check this out. If you reduce these, the probability of an ace is actually 1 out of 13. And the probability of a diamond is 1 over 4. And those numbers should look a little familiar. Sorry, I got something on here. If you look at these are the exact same numbers. So the fact that it was a diamond doesn't change the possibility of me getting an ace, because those are the same. Or the fact that the card was an ace doesn't affect the chance, the likelihood that it's a diamond. So do you remember what we call those kind of events where one does not affect the other? Sounds and looks like no, we don't remember what those are called. Those are called independent. There we go. Thanks, Carolina. So those are called independent events. So drawing a diamond and drawing an ace are independent. Meaning one of them does not affect the other. And so this is the check for independence. You look and you see, is the probability of the one happening on its own the same as the one happening given that the other has occurred? And if those two numbers are equal, you know that they are independent. Okay, well, I just wanted to bring that up as a refresher about right there. Okay, so how are we feeling about probabilities? Is it making a little bit more sense? Now we've seen some examples. Give me a thumbs up. If it's not making more sense, yell at me. Do something. Oh, all right, it's looking like we're feeling pretty good. All right, let's take a real quick break. I need to go get a drink and use the restroom. So I'll come back in 5 minutes. That looks like 5:07 on my clock. And we'll talk a little bit more about some graphical ways of seeing these things, some things called like tree diagrams and Venn diagrams. And then we'll move on to binomial distributions. All right. So come back in 5. You'll know I'm ready when you see this image again. All right. So see you in just a few. All right, so let me show you a couple of visual ways to help you with calculating probabilities and seeing these sets and things like that. And I'm really going to show you 2 different kinds of diagrams. One's called a Venn diagram, and the other is called a tree diagram. And both of them have their uses, kind of depending on what you're doing, is how you decide which to use. So let me start with a Venn diagram. So it's spelled V-E-N-N. It's actually named for, I think it was a Dutch mathematician who came up with this. But we got a Venn diagram. Now, what every Venn diagram has, like a little box like this, and then we have some circles on the inside. Now, I'm going to show you examples with just 2 circles, but you can have more than 2. You can have 3 or more. And we overlap the circles. All right, now, here's how these play out when it comes to probabilities. So this is especially useful when you have two events. The circles are those two events. If you have three events, you would throw in a third circle and so on. All right, but these are two events. So let's just say that this one on the left is event A, and the one is event B. Now, all the possible outcomes are somewhere in this rectangle. If they are outcomes that are event A, they lie within the A circle. All right, so let's go back to that example of the men, women, yes, no thing. We could say, okay, A would be all of the men. Let's say one of the events is men. So the men would all be in the circle. And let's say B was the people that said no. So you can imagine we're in a room and I tape on the floor two big circles. And if we were actually together, I would do this so we could experience it. But I'd make two big circles and I say, okay, I want all of the men to get in circle A. And I want all the people that said no to this question to get in circle B. All right, now, does that mean that everyone's going to be in a circle? Are there going to be people that are not in one of the circles? Is anyone back? No, I'm not sure if I'm just talking to a wall or not. Well, how about this? What if you're a woman? Well, you're definitely not in A. If you said yes, you're not in B. So if you're a woman who says yes, you're somewhere outside the circles. Well, what about the man who says no? They have to be in circle A and they have to be in circle B. And the only way they can do that is if they're in this region that's in between. So this overlapping region right here, that's actually A and B. So you can maybe start seeing how this can help you graphically. Because if we're looking for, say, the probability of A and B, we just have to look for how many are in that overlap. So Bruno, you just said, would that mean that there needs to be more circles to account for everyone? Actually, no, this would be good. This would be enough. Let's go back to that list of numbers. And unfortunately, I don't remember what they were on that contingency table. I know that the women were 40 and 10. I think it was 22 and 28. If not, we're going to go with those. All right, so here's where everyone would be. So if we say that in this case, this Venn diagram, that A is male and B is, they said no. So in this overlap, A and B, there are going to be 28 people standing in there. Those 28 people were the 28 men who said no. They have to be standing in both circles. All right, on this side, the rest of A, this is the men who did not say no. So the men who actually said yes. And so there are going to be 22 of those. Corresponding to that set. All right, now over here, we need people who said no that are not men. Well, those are going to be these 10, right? The women who said no are going to be over here. Now, outside of these double circles are the people that did not say no, so they said yes, and they're also not men. So to not be in these circles, you have to be female, and you have to have said yes. All right, well, that leaves the remaining 40 who are not in either circle. So all 100 of the people are accounted for. They're all somewhere. But the two circles, I only have those two circles because I was interested in these two events. Men and you said no. Those two events. If I had a third event, then I would need to make another circle. And it might get a little bit more complicated in terms of where people are located. But for these two events, no, everybody's got a spot. Your spot just might be outside of the circle. So does that answer your question, Bruno? Did I kind of cover that? Yeah, okay, cool. So here's how you get the probabilities then pretty quickly. It's just a matter of adding up the numbers. Now we already had it in a contingency table, so it's pretty simple to see, but if it was in a Venn diagram, here's how we would do this. Like let's say we wanted the probability of male. Well, the male are the people in the circle A. Well, the circle A has 22 plus 28 out of the total of 100, so that's 50 out of 100. Or what if I wanted the probability of no? Well, the no's, there are these 10 and 28 that are in the B circle. So 28 plus 10 divided by the total number of people all together, which is 100. So that would be 38 out of 100. If I want to know the probability of male and no, I look for the overlap. That's 28 over 100 and so on and so forth. So Venn diagrams can be really useful because they definitely also show the overlap. Anything that's a member of both goes into that overlap region. And it's important to see that. If there's nothing in there, if this is blank, then we know they're mutually exclusive, right? But male and saying no are not mutually exclusive. There are members of both. There are 28 people, actually. They were both male and said no. All right, so this is the idea behind a Venn diagram, and it's just a visual way of having all that information from a table given specifics, right? We had to say what our events were, that A was men, B was they said no. Because if we were going to be looking at something different, it would be a completely different picture, same picture, but different numbers. So you can always start with the picture of the two overlapping circles inside a rectangle, but what numbers go where, that depends on how we define our events. All right, so there's a Venn diagram. The other thing that we can use that's kind of helpful, especially when we're trying to calculate how many different possibilities there are for different events, is what we call a tree diagram. And a tree diagram is exactly what it sounds like. It's branches of a tree. All right, and to give you an example as we kind of build one of these, we're going to look at tossing a coin. All right, and basically this is going to be branches of a tree, quote unquote tree, that show all the possibilities. All right, so here's our example. We're going to toss a coin 3 times. And what we're going to do is we're going to keep track of all of the different possibilities as we toss that coin. Okay, we're going to, and we're, for the sake of us, we're going to assume that it's a fair coin, that heads and tails are equally likely. But even if they're not, we can still use the tree diagram. All right, let me just grab a coin. I see I've got one on my shelf. It turns out this is a 5 peso coin from Mexico. Clearly, I got it when I was in Mexico sometime. All right, so we got a heads and we got a tails. So I'm going to toss it, right? Catch it, heads or tails. All right, so what are our different options here? Well, there are 2 possibilities. I either get a head or I get a tail. So here's how I'm going to start my tree. For the first toss, I have 2 possibilities. I can get a head or I can get a tail. So I'm going to write them as H and T. All right, now suppose that first toss I got a head. Right? So it lands. Okay, cool, I got heads. I toss it again. I have 2 options yet again. After that first head, I can get a second head or I can get a tail. Right? So on my second toss, these are the possibilities given that first head. All right, well, same thing for that tail. If the first time I toss it as a tail, the second one still can be a head or a tail. So I've got 2 options there. All right, well, I think you see what's going on here. On my third toss, I could have gotten heads and heads, and then 2 options, heads or tails. This one, 2 options, heads or tails. 2 options, heads or tails. 2 options, heads or tails. And so you can start seeing the tree. Right? These are the branches of a tree. It's more like it's an upside down tree, right? We usually think of those branches as going up, but mathematicians are not very creative. So the fact that we even call it a tree diagram, you got to give us props for. So, all right, now here's the whole point of this. This is a real visual representation of the different possibilities. We just follow these branches starting at the top, and we work our way down. And we work our way down, and we work our way down all the different ways. And you can actually make a list of all the possible outcomes. So think about this one. If I just went down this first branch, going this way, that was, I got a head on the first toss, a head on the second toss, and a head on the third toss. So one possibility here is heads, heads, heads. I got 3 heads in a row. Hey. All right, now if I follow these branches, but then instead of going straight down, I turn. So let's just kind of go this way. I'm going to go down here and then turn down that branch. This one is heads, heads, tails. So I got 2 heads and then I got a tail. All right, well, keep doing this process. So now I'm going to follow that branch down. That was heads, tails, heads. I'm going to do one more and then we'll just sort of speed it up. And then I follow this path down. That was heads, tails, tails. All right. So instead of just keep drawing them all, I'm going to jump straight to the what do we get with each one of them. So this next one is going to be tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. All right, so here's how this helps us with probabilities. Suppose I asked you this. What's the probability of getting 2 heads? So I toss a coin 3 times, and what's the probability that twice it comes up heads? So think about what we need. We need to know 2 numbers. One, we need to know how many of the tosses give us 2 heads. And then we also need to know how many total possibilities were there in terms of different outcomes tossing the coin 3 times. Okay, so let's start with the getting exactly 2 heads. Not the first one, but the second one that works, right? I get 2 heads here. I get 2 heads with the next one. Not this guy. That one's got 2 heads. 1 head, no heads. So the probability of getting 2 heads, there are 3 events where I get 2 heads. And then what about the total number? Well, let's count up how many total branches there were on this tree, like at the very bottom. There's 1, 2, 3, 4, 5, 6, 7, 8. So there are actually only 8 possible outcomes when we toss this coin 3 times. So I don't know, I didn't catch who that was. I think that might have been Ali put up 24. And I totally see where your 24 is coming from because you're looking at all of the HTs here. But yeah, you want to think about it as like this head is one outcome. Even though it's made up of 3 different coin tosses, it's one outcome. It might help if you think about it as, what if I'm tossing 3 different coins? Luckily, my desk has everything on it. So here are 3 different coins. So I've got a 5 peso that you saw before, a 1 peso, oh yeah, and a penny. All right, so think of each of those as a different coin, but I toss them all at once. We could also think of it as penny, 5 peso, 1 peso, right? Whatever. So the act of tossing them all at once gets me the one event. So this one, the probability of getting 2 heads, getting exactly 2 heads, is 3 out of 8. All right, so 3 out of every 8 times you should get 2 heads. So what's the probability, say, of no heads? What's the likelihood that if I toss this coin 3 times, that I get no heads? Well, the bottom number doesn't change. There's still 8 total combinations. How many of them are no heads? Yeah, just the one, where I get tails, tails, tails. So it's much less likely, it's 3 times less likely, that I don't get any heads whatsoever. All right, so tree diagrams are really useful when you know what the different options are. And you can create branches for all your options and go down them. Another way that you can get this probability without actually counting it up is this. So think about this. What's the probability that I get a head? If I toss a fair coin, what's the probability that I get a head? It's not a trick. We have two options. One of them's a head. So the probability is 1/2. So what we could do is, if we wanted to, we could just write the probabilities. This one's 1/2. This one's 1/2. This one's 1/2. Tails are also 1/2, right? So all these things have a probability of 1/2. So if I want to know what the probability of getting 3 heads is, it's 1/2 times 1/2 times 1/2. Or the getting no heads, that's getting a tail each time. That's 1/2 times 1/2 times 1/2. So if you have the probabilities, you can put the probabilities in for your different pieces and then multiply them together. And that gets you your probability of reaching the bottom of that branch. So while we're here, let's go ahead and just build a probability chart for our different possibilities, because we're almost there anyway. We've got just about, well, we got half of them. But here's what we're gonna do, right? Let's go with the number of heads and what our probability is. So we can get no heads, we can get 1, we can get 2, or we can get 3. Now we already calculated the no heads is 1 out of 8. The 2 heads was 3 out of 8. All right, 3 heads only happens 1 time. So that's 1 out of 8. And 1 head, if we count those up, there's 1, 2, 3 of those as well. So that one's also 3/8. This is the other nice thing about a tree diagram, is it's really easy to calculate the probabilities of all the different outcomes just by adding them up. Okay, so Venn diagrams, tree diagrams, they're both useful depending on what you're doing. And they're both really good visuals for what we're looking at. All right, so now that we've talked about probability, let's start aiming ourselves towards using probability for doing statistics. So the next thing I need to show you, or what we need to talk about, are what we call probability density functions. So let me just write this up here real quick. All right, so probability density function is a mouthful. So what we'll usually write is PDF. So in the context of stats class, PDF means probability density function. Okay, so this is a function. You remember functions in math, I hope, right? The idea behind a function is you plug a number in, you get something out, right? You plug something in, you get something out. Probability density functions, what they do is you put in your event, you get out the probability of that event. All right, so what we need, anytime we do a probability density function, is we need a random variable. And in general, we use a capital X when we're talking about a random variable in statistics. And a random variable in statistics is not what you think of as a variable, right? You think of a variable in math as a number, right? It's a number you plug in. But remember, in stats, that's not what variable means. You remember what a variable is in stats?
It's a placeholder.
It's not a placeholder. That's what it is in algebra. Go back and look at quiz 1. Remember we had all those terms that we like data, parameter, population. Variable was in there too.
It's a characteristic we are measuring.
Yeah, it's the thing that we're measuring. So when we do this and we define a random variable, we usually use words for it. Right? So for example, with this one where we're doing the heads and all that, this guy X in this case, so capital X, it's the number of heads okay, so it's the number of heads that we get when we do this. It can take on the values of 0, 1, 2, and 3, but that would be the variable. That's what we're measuring. How many heads do we get? Right? That's the characteristic we're looking at here. It could be, what is the average height of 5th grade boys? It could be, whatever, right? But we tend to use words to describe what it is. All right, now, it turns out that with probability density functions, it depends what kind of event is going on. And so we're going to break this into 2 different types. There are continuous and discrete. All right, so we're going to have discrete PDFs, and we're going to have continuous PDFs. So what's the difference between discrete and continuous? What did we see before? Again, consult quiz 1.
Discrete numbers are countable. They're whole numbers. Continuous, you can't count them. Fractions are decimal.
Cool, perfect. So discrete means countable, whole numbers. Continuous means you can get decimals and fractions and whatever else, but you can't count them. Okay, so it's the same as before, discrete versus continuous. So this one with the number of heads, this one's discrete. We can count how many heads we got. If we're talking about the average weight of, puppies born, in a pound, that's going to be continuous because they can take all kinds of different ranges, it's not countable. So we need to know if it's discrete or continuous because we do things differently depending on it. So we're going to start with discrete because discrete are a little bit easier. They're a little bit easier to do. Now, if you have a discrete probability density function, 2 things have to be true. Okay, the first, so I guess these are going to be 2 facts for discrete PDFs, right? The first is that the probability of each outcome is between 0 and 1. Okay, so I'm going to put here that all outcomes have a probability between 0 and 1. Again, 0 meaning cannot happen, will not happen. 1 meaning will definitely happen. All right, but all the outcomes have to have a probability between 0 and 1. And the other fact is that the sum of all of the probabilities equals 1. So if you look at all the possible outcomes in our discrete, like all the different options, those probabilities add up to 1. So I left this chart here for a reason, because I'd like you to look at the probabilities for these different events. So we calculated them, we saw them. Notice that they are not less than 0, they're not negative, and none of them are bigger than 1. So we can put a check mark next to the first thing. All the outcomes are between 0 and 1. And check out what happens if we add up all the possibilities. If we take 1/8 plus 3/8 plus 3/8 plus 1/8, got our nice common denominator of 8. But you add the tops, 1 plus 3 is 4, plus 3 is 7, plus 1 is 8. We get 8/8, which is 1. So this is a discrete probability function. So this is exactly what we're talking about. We're looking at things like this. All right, so let me give you another one. This is completely unrelated to tossing coins. And this has everything to do with baseball, which just so you guys know, because we're starting to get closer and closer to spring training, I will talk more and more about baseball because I'm a fiend for baseball. I love it. But if you don't like baseball, it's fine. Don't worry about it. I will think poorly of you, but I won't let it be shown. Right? It'll be internal. I'm just kidding. Anyway, so if you look at the World Series, to win the World Series, you have to win 4 games. And so there will at least be 4 games played in the World Series. It's possible that you have to play 7 games. And that's the most that can happen, right? Where it's 3-3 and then somebody gets 4 in the 7th game. So every World Series is either completed in 4 games, 5 games, 6 games, or 7 games. So I actually went and I looked, how many games did each of the last 40 World Series go to? So I went all the way back to 1979 to see how many games it took. And so I've got those frequencies. So let's look at probabilities, given this data set. What's the probability that it's going to go 4 games, 5 games, 6 games, 7 games? So let me go ahead and give you the data. So this is the last 40 World Series. All right, so this is the number of games that were played and the frequency. I'm going to make another chart or another column here for the probability. We'll calculate those in a second. All right, so it either goes 4 or 5, 6 or 7 games, and these are real numbers. I am not making this up. You can go and do some data mining and find this. But these are the frequencies. So in the last 40 World Series, 8 of them were sweeps. 8 of them were done in 4 games. 13 of them required all 7 games, required the maximum number of games. Right? And then 5 and 6 are in there as well. All right, so with this information, what's the probability that it's going to take 4 games? Well, it happened 8 times out of 40. So that's 8 out of 40. 5 games is 9 out of 40. 10 games, or 6 games is 10 out of 40. And 7 games is 13 out of 40. So each of those probabilities is between 0 and 1. And if you add them all up, you will get 1. All right, so these are discrete probability density functions because we're getting only countable results. Right? Okay, so one of the things that we're interested in when we have probabilities and stuff like that is what we call expected value. So I'm going to show you expected value and then we're going to call it a day. So remember this for the heads probabilities. We'll come back to them because I want to look at the expected value of those. But here's what here's how we define expected value. The way we calculate expected value is that it's a sum of the probability times the value of our variable. So I'm going to write this as the sum of p times x. So x is our variable, which in this case is going to be number of heads, number of games, whatever. So I'm going to multiply those times their probability and then add them all up. So this is the definition of the expected value. I know it probably doesn't really mean anything to you right now, but let's find the expected value for the World Series. And then in the context of that, I'll explain what it means. All right. Actually, let's do the coin toss one first. Let's do the coin toss one first because it's got easier numbers. All right, so let's go back to the coin toss. So here's how we're going to get our expected value. We're going to take the probabilities times the outcomes. So think about we had 4 different outcomes available for our variable. We could get 0 heads, 1 head, 2 head, or 3 heads. Okay, so 0 heads happened 1 out of every 8 times. So I'm going to write 0 times 1/8. 1 head happened 3 out of every 8 times. 2 heads also happened with a probability of 3/8. And 3 heads happened with a probability of 1 out of 8. Okay, so it's a sum. Remember, this thing means sum, so I'm adding stuff up. And what I'm multiplying together are the values times their probabilities. All right, well, let's add this up and let's see what we get. So this expected value is going to be 0 plus 3/8 plus 6/8 plus 3/8, which is 12/8 or 1.5. All right, so no context to it whatsoever. That's our expected value, 1.5. Okay, so what the hell does that mean? Yay, it's our expected value. We'll use the name. Expected. When you expect something to happen, you're like, oh yeah, that's what should happen. That's the expected result, right? I expected that the Kansas City Chiefs were going to win the football game. right? It's what you think is going to happen. If something's unexpected, you're like, whoa, where'd that come from? Okay, so it's an expected value. When we say value, this is the value of the variable. So expected value means long haul. If we do this a lot, this is what value the variable should take on. So in the case of the coin toss, remember what our variable was? It was the number of heads, the number of heads that we should get. So what this is saying is that over the long run, we should get on average 1.5 heads. Now, are you ever going to get 1.5 heads? No. It's going to be 1, or it's going to be 2, 0, or 3. But over the long haul, we should expect numbers around 1.5. So that's exactly what expected value means. How many of them should we get? So if we look at the World Series data, think about what this expected value is going to be now. It's going to be the expected, what we should get for the variable, which is the number of games in that World Series. So when we calculate this, when we get a number, that's going to tell us, you know what, on average, basically, on average, the World Series is going to go this many games. So let's calculate it. Let's see what that number actually looks like for the World Series. So I'm going to take the results, the number of games, and I'm going to multiply it by the probabilities. And then I'm going to add all those things up. Okay, so here's for the expected value of number of games played in the World Series. All right, so 4 games has a probability of 8/40. 5 games has a probability of 9/40. 6 games had a probability of 10/40. And 7 games had a probability of 13/40. So let's do those multiplications. So we're going to get 32/40 plus 45/40 plus 60/40 plus 91/40. And then I need to add all those up. So since it's got the common denominator of 40, I can just leave that. And I end up, if I add them all together, I get 228 out of 40. But let's go ahead and get a decimal for that. So if I take 228 and I divide it by 40, I get 5.7. All right, so that's the expected value. But again, interpreting what it means on average, the World Series takes 5.7 games to complete. But remember, that doesn't mean that a World Series takes 5.7 games. In fact, it can't. And that's the thing about discrete. probability density functions, a lot of the numbers that we get when we calculate means, standard deviations, all that kind of stuff, they're going to land us in between possible values quite frequently. That's not going to be a problem with continuous. When they're continuous, right, if we're talking about, the weight of something, 5.7 is perfectly appropriate. But because this is discrete, we lose that. So just realize that we're going to get numbers that don't match our discrete values. And that's okay. It's totally okay. But this is an expected value. So next year, when the World Series happens, I'm going to expect that the number of games that it requires is going to be near 5.7. Since it's discrete, which number would I say? What number of games do you think is most likely? 4, 5, 6, or 7? Or what is expected? Yeah, thanks, guys. How about 6? Why 6? Because it's closest to this. So if you were a gambler and someone said, all right, hey, let's put money on how many games the World Series is going to go. And knowing nothing, you don't know what teams are in it, you don't know anything about it, you're going to want to bet on 6 games. Because that's on average most likely to occur. Right? Now, that's long-term expected, but for any one, we see that it's actually 7 games is the one that's most frequent, which actually doesn't surprise me as a baseball guy. That just means those 2 teams are really evenly matched, and so it's going to go the distance, right? But on average, it should take 5.7 games to complete. So expected value. What do we expect to happen? The series should go around 5.7 games. All right, so there's expected value. All right, well, I see we're out of time, so I'm going to go ahead and call it a day. In terms of where we are and where we're going, a couple things. A, make sure you keep working on getting your group together for a project, because the time is a ticking. We'll definitely talk about it at length on Tuesday, but and we're going to keep going. I'll introduce you to the binomial distribution, which is a discrete probability density function. We'll play around with it, and then we'll continue our discussion of density functions. All right, so with that, I'm going to go ahead and stop our recording and wish you all a great weekend.